Alright, welcome back. This is the fifth part of this very long lecture. In the first four parts of this long lecture, we were only talking about in situ observations, and remote sensing is going to be our other strategy for getting meteorological information. Now, if you just pull up a definition of remote sensing, you get that it's the scanning of the Earth by a satellite or high-flying aircraft in order to obtain information about it. I don't like that definition at all because it excludes a bunch of things that are great examples of meteorological remote sensing. That is a there's a radar inside of that big dome that you see at that National Weather Service office over there on the left. Radar is a brilliant example of remote sensing. We are detecting precipitation far from the location of the instrument itself. We're going to learn, for example, today about different instruments that can measure winds and other properties of the atmosphere at some distance above the surface of the Earth. There's some kind of wind profiler there on the left. That is a HAT Pro on the right. A HAT Pro is actually a brand. They measure moisture and temperature profiles in the atmosphere, again, without actually touching the atmosphere. They're down there at the surface. So in the context of remote sensing, we need a better in the context of meteorology, we need a better definition of remote sensing. And I would say that remote sensing observations are measurements that are taken by instruments that are not touching what they are measuring. They are remote from the phenomenon that they are measuring. And again, we're going to work our way through a little list of these kinds of instruments, with the first one not exactly being an example of an instrument, that's just the Doppler effect. Now, I don't know what you bring to this class in terms of like your knowledge of physics or high school physics or something like that. The Doppler effect is either something you totally get already, or you haven't seen in a really long time or something like that. Your book has certainly a very simplistic explanation of the Doppler effect and how we can use the Doppler shift to determine properties. But I like to use the example of like a police radar gun. Police officers monitor the speed that vehicles are traveling using a radar gun that emits microwave radiation. The radiation reflects off of a moving object like the cars around them, and when that reflection happens, the wavelength of the radiation that the gun emitted changes. That's the nature of the Doppler shift, and again, your book has a nice explanation as to how that all works, but by measuring the shift in the wavelength of the radiation after it has been reflected off of the moving object, you can determine the speed of the object. Or at least that's usually the explanation that you get by watching, high school science lectures or Bill Nye the Science Guy on Netflix or something like that. In a little detail that's sort of missing there is it's actually only the component of the motion that's inbound or outbound along the line of sight of the instrument itself. The cross-track measurement of the speed doesn't work at all. That's why the police, when they're monitoring the speed with using like a radar gun, they usually like hide under a bridge or overpass or something like that, or park behind the road. They need to be shining the beam up and down the road. They cannot measure the speed of cross-traffic, only the stuff that's in and up and down the line of sight of the instrument. We use Doppler effect and the Doppler shift of wavelength quite a lot in remote sensing. This is an example of Doppler radar. This is a Doppler weather radar station. You can see the site of the station over there in Dodge City, Kansas, where the black dot is. And on this particular plot, Doppler radar reflects off of raindrops in the atmosphere. And on this plot, red is how we're coloring raindrops that are outbound and headed away from the radar dish, and blue and green in this case happen to be inbound. And so if you actually plot the most interesting looking feature on here, where we have reds and blues right next to each other, and we see that we have a tight little area where there's strong outbound wind right next to areas where there's strong wind with an inbound component, well, that's actually showing us rotation. The Doppler radar cannot see this cross line of sight part of the circulation, but it's indicating to us that we're seeing this very strong rotation. In fact, probably you're not terribly surprised to find out that that's a tornado that we're seeing on there, where we're seeing the very strong rotation. The Doppler radar really only sees the inbound and outbound components of the rotation, but we can kind of put two and two together and figure out that that is rotation. So this Doppler shift is going to form the basis of much of what we call in meteorology active remote sensing. Now, active remote sensing is when you have an instrument like a radar station or a Lidar or a Sodar or whatever emit some form of energy, usually radiation, and have it reflect off of some kind of target, like raindrops, or dust, or aerosols. Those are little specks of solids and liquids in the atmosphere, or so on. In the atmosphere, you have it reflect, and based on the properties of the reflected radiation, you're going to be able to infer parameters about the environment, like rain rate, or the direction of the winds, or whatever. But the key to it being active remote sensing is the instrument is actually giving off the energy. The radar dish emits the microwave radiation, which then gets reflected off of raindrops. Now, our first example of one that has nice applications in wind energy is Lidar. Lidar is an abbreviation, an acronym that comes from Light Detection and Ranging, which seems like a very awkward name until you realize that that's where the word radar comes from too. Radar is an acronym for radio detection and ranging, so we just sort of borrowed the same terminology here. And Lidar works using the Doppler effect, and it uses the type of energy that it's using is laser light. It shines a laser light upward into the environment, and it reflects that laser light. It's at appropriate wavelengths of energy that it reflects off of dust and aerosols in the atmosphere. Now I'm going to try to put together a little picture here to help you understand what's going on. Here's my Lidar station at the surface. It doesn't just emit a single laser up. There's actually 4 lasers that are pointed kind of up, but also a little bit at an angle, typically oriented to be the 4 cardinal directions, one going north, south, east, and west. And in this case here, I'm just drawing what I think the actual wind air is supposed to be. And if that laser beam hits a dust particle in the Earth's atmosphere, well, that dust particle is moving. It's moving with the wind. We should be able to use the Doppler shift when those photons of laser light hit and reflect off of that dust particle to infer the speed and direction of the velocity. Now I'm going to use my little magnifying glass tool to zoom in here on that little dust speck right there. And that black arrow that's on there is the true motion of that dust aerosol, and therefore the wind. But that's not actually what we're seeing. I mean, we could take that motion there, that black arrow, and we could partition it into 2 component vectors. One being in the direction of the laser beam itself, along the line of sight of the laser beam. That's that short yellow laser arrow right there. And the other is the cross-track component that is perpendicular to the laser beam itself. So we could take the real wind and we could divide it into those 2 yellow components that I have right there. And the reason why we have to do that is that short yellow light laser, that is what we are measuring using the Doppler effect. When we measure the Doppler shift, what we're getting is that short yellow component of the actual motion. The longer yellow component is still unknown. We don't actually measure that using the Doppler shift on a LiDAR. And neither of those are what we want. What we want is that black vector that is the actual motion of the aerosol and therefore the winds. So we get a piece of information from the LiDAR, but that's not really what we want. But if you make certain assumptions, most notably that there's no net vertical motion going on at the time, which is not a terrible assumption averaged over time, and you use a bunch of trigonometry to figure out all the angles and so on, you can actually solve for the motion of that aerosol and therefore the wind. You can actually solve for that black vector right there. It's not easy. It involves a bunch of assumptions, but the errors cancel out over a large sample of aerosols, which is exactly what's going to happen. You're going to be measuring this over there's thousands of aerosols in a cubic centimeter of air. So averaged over large samples, the errors are canceling out, and you're going to get a measure of the wind, well, at least the component of the wind in the direction that laser is tipped. So if that was like the laser pointing a little bit to the north, now you know that component of the wind. Do this over 4 lasers pointing, again, mostly up, but kind of in slightly tipped towards the 4 cardinal directions, and you get the complete vector of the winds. And this is a pretty slick trick. This is a good technology for measuring the winds, and we can get the winds through about 200 meters above the ground. We can't do this all the way up to like the tropopause or something. In fact, we can't even get out of the boundary layer with LiDAR. But low-level winds, this actually works pretty well. And actually, 200 meters, that's a pretty good range of heights for things like wind power applications. That's about in the range in which we're talking about the volume of air passing through the turbine of a windmill. So this makes a measure of sense. This is a good technology for this. Now, a little detail here that comes from LiDAR is this isn't exactly a point measurement. This isn't the same as like what you get from a cup anemometer. A cup anemometer gives you the winds right there at the location of the cup anemometer. This is more like the integrated or average wind over that whole cone-shaped area that the Lidar is probing there. And that's kind of a problem if you're using this for like meteorological research or for flight operations for an aircraft or something. But actually, that's not a bug, that's a feature when we're talking wind power, because that's actually kind of what we want. The winds that are passing through the wind turbine aren't just a point. We don't need to really know what the wind is at one point. We kind of need to know what the broad average winds over like a layer are. And so actually Lidar is a great tool for the job in wind power applications. Now in the case of Lidar, the energy that was being emitted in this form of active remote sensing was laser light. Now there is a different technology we could use called Sodar, where the energy being emitted is actually sound. Sodar stands for Sound Detection and Ranging. It's just an awkward acronym to make sure it sounds like radar and LiDAR and so on. And everything I just did there using that light, instead just use sound waves. And, when the sound waves reflect off of the aerosols and dust in the atmosphere, they're going to have a shift in the wavelength of the sound waves. There'll be a change in the pitch of the sound. And by listening for the echo of the sound waves instead of the reflected light, the way you would with LiDAR, you can actually do the same calculations we did with LiDAR and use Sodar to determine the winds in the lower part of the atmosphere as well. And you might be thinking this can't possibly be right. But I'm going to show you right here. This is actually a video I just snatched off of YouTube here. And you can actually listen and hear the sounds that the Sodar station is making. Isn't that wild? I mean, the thing is actually quite noisy. You can't actually operate a Sodar station anywhere near like residences or anything like that. But for certain applications in certain environments, this is a really good technology, and there are pros and cons of using Sodar versus LiDAR and LiDAR versus Sodar. It depends on a number of factors of the environment you're going to be working in and so on, but they provide very similar information about the winds in the lowest couple hundred meters of the surface of the Earth. That's another type of Sodar, by the way, in the picture there. It's just amazing to me how it just looks like a giant bell that's making these noises. While I'm on the subject of LiDAR and Sodar, I'm going to talk about it real quick, another technology which is called wind profilers. Wind profilers are very much like lasers, like LiDAR, but it's not a laser type of light. It's a different part of the electromagnetic spectrum, and it's not, it doesn't have all the fancy properties that laser light does, about the way the light photons are modulated and so on. But it's a similar sort of idea in that, again, there are 4 beams going up and you are determining the component of the flow in each of the directions of those beams. It's the same sort of calculations, but this has a much greater range. Wind profilers can measure the winds at least several kilometers above the surface of the Earth, and they use pulses of radiation instead of being in a continuous mode where they're just continually emitting the radiation. LiDARs and so on have a pulse mode too, but that's not typically how we use them. So like the wind profiler will emit a pulse of radiation, and then depending on how long it took for the radiation to reflect off of the dust and aerosols in the atmosphere and return back to the surface of the Earth, we know how high up we're talking about. We can actually derive a profile of the winds using wind profiler technology, hence the name. And I thought I'd show you actually the research that I do in West Africa. Actually, we use wind profilers, which, by the way, it's totally astonishing to me that there's wind profilers in West Africa, but that's another story. So like, for example, this is a diagram of wind profiler data over a 1, 2, 3, 4, 5-day period. You can see the time is on the x-axis, and height above the ground is on the y-axis. And the wind profiler has to be able to get reflected radiation off of particles in the atmosphere, and there aren't always those particles there, which is why there's plenty of white area on the map where the profiler just wasn't getting enough reflected radiation to do anything with. But from there, you can see those wind vectors on there. Now, the vectors are actually drawn on there to be like on a map. So like if they're going from right to left on the plot, those are supposed to be an east wind. And if they're going from the bottom of the plot towards the top, that's supposed to be a south wind. And, I mean, I'm not expecting you to get anything particularly out of this, like, oh, actually, I can see the African easterly jet just fine at about 3 kilometers above the ground on the 11th and 12th of August of 2006. I don't expect you to know or care about that, but the idea that we can have a profile, I mean, good grief, sometimes we're getting these winds all the way up to a height of about 6 kilometers up in this particular case, and I think they have modes that can go up to as high as about 14 kilometers on that particular wind profiler. Yeah, this exists. It's a real thing. And in fact, we operate a network of these in the United States. This map here just shows you the locations of 2 different types of wind profilers. Don't worry about why there's circles and why there's stars at different locations, but you can see some of them are actually not terribly far from Omaha. You can see there's one in Neely, Nebraska, for example. And they're, used to come up with profiles of the wind. I'm not sure what the time resolution of these profiles are in the ones they use in the United States. The ones that we were using in West Africa are about every 10 minutes it takes a wind profile. Just for power needs and stuff like that. There was only so much power to use. We couldn't take a profile like every minute or something like that, but there's no technical reason why you couldn't. So I would suspect they actually use higher resolution in the United States. And they principally use them in the United States for forecasting severe weather. We get data from these wind profilers almost continuously, whereas like data from weather balloons and radiosondes we only get twice a day, and from much fewer locations, not nearly as good of resolution spatially as we get from these wind profilers. Another piece of technology that's an example of active remote sensing and that I love are salameters. Salameters, that is a hard word to say. It's not celiometer, it's salameter. And it is used to measure what we call the ceiling in meteorology. Ceilings are the base of the clouds. That term ceiling actually comes to us from aviation. When they're taking off, the pilot wants to know how low is the ceiling, so that it can, knows how high it will go up before it hits like the base of clouds and so on. Salameters are a pretty straightforward piece of technology. They just shine a laser light upward. They actually do it in little pulses, and when the light reflects off the base of the clouds and returns to a sensor inside of the salameter housing there, we could actually use the time it took for that pulse to travel there and back to measure how high was the base of the cloud. And we use them actually quite a lot. In fact, that's the core of what I do with my research, is working with salameters in West Africa. Here is, for example, again, a plot from, just as an example from my research here, where this is salameter output, where time is on the x-axis. Now, on the x-axis, that's just hours. So that's one 24-hour period on the x-axis there, versus height. And as clouds came by the salameter, it's just measuring the base of the clouds, what is the bottom of the clouds. And you can see, starting at about 5 o'clock in the morning, there were these really thick, these clouds that were extremely close to the surface of the Earth. I'm fascinated by these very, very low clouds. We can't tell anything about how thick they are, but we can measure that their base is, something like 70 meters above the ground. And then once the sun comes up around 7 or 8 in the morning at this time of year, you can see how the base of the clouds is getting higher above the ground, and they're also getting less continuous. You can see how there's little gaps between the clouds as we get to 10 o'clock and 12 o'clock and so on. And then they completely burned off by mid-afternoon around 1500 hours. That is just, from a tropical meteorology perspective, totally cool. But we use these things all over the place for measuring the heights of clouds. Every airport in America Congress has paid for a salameter to be measuring the heights of the clouds and so on. This is a very standard piece of meteorological equipment. They're not terribly expensive, they're not terribly hard to keep calibrated, etc. Now, the last chunk of instruments I want to talk about are the ones that are on board meteorological satellites. Now, this is a hard topic to talk about in 5 minutes, because there are entire courses at Creighton that are about satellite meteorology and satellite remote sensing of the environment and so on. I mean, there are literally dozens of different kinds of sensors that can be on board satellites on all kinds of different orbits, when these satellites can go in polar orbits or geostationary orbits or all kinds of crazy orbits. They can be measuring different properties in the atmosphere, from winds and rainfall rate and cloud coverage to inferring temperature profiles and humidity profiles in the atmosphere and so on. Most of these satellite remote sensing techniques are an example of what we call a passive remote sensing technique. Passive remote sensing is when you measure the radiation that is just naturally being emitted by the object. All objects, air, clouds, the ground, you and me, we're all emitting radiation all the time. And by measuring that radiation's properties, like the amount of radiation, the wavelength of the radiation, its polarization, and so on, there's a whole bunch of properties or parameters of the natural environment that we can infer. Again, like rain rate, or wind speed, or temperatures, or sea surface temperature, or something like that. It's a passive way, though. The satellite is in general not emitting the radiation that gets reflected off the ocean surface, and no, most of the time we're talking about radiation that's being emitted by the surface. Although this now, I mean, again, most of these satellites are using passive remote sensing, but actually working together with passive and active remote sensing is a huge deal right now. In fact, here's just a screenshot of NASA's global precipitation measurement page, which is a whole constellation of satellites. I love that word, constellation. A constellation of satellites mean like a whole group of satellites working together. Some of the satellites are passive remote sensing, measuring the radiation actually emitted by like raindrops and ice crystals in clouds and so on. And some of these measurements are actually active remote sensing. There's actually satellites up in space that have radar that are emitting down towards the surface of the Earth, measuring the precipitation inside of those clouds. And we're finding ways to combine active and passive remote sensing data from like a whole constellation of satellites is like a huge growth area in like NASA-funded research right now. Okay, so getting these kind of beautiful, new high technology stuff to work is totally cool. For more wind applications, I thought I'd just show you real quick. Over open oceans, measuring the surface winds are actually not terribly difficult at all. Satellites can infer those surface winds over the ocean because the ocean changes its roughness in response to the speed of the wind. I don't want to say that the satellite looks down and can see like the waves or something like that. This is a much more microphysical property. It has to do with the polarization and scattering of the microwave radiation that it's emitting. That can actually tell things about the roughness of the ocean, and from that, the wind speeds that it took to maintain that roughness. And you can see, I don't know how well in the YouTube video this will show up, but you can see that, like, this is off British Columbia on a particular day, and the satellite was figuring out the winds. Those little symbols there are just little wind barbs. They point in the direction the wind is going. And you can see there's little circulation, cyclones and anticyclones and stuff like that going on at the surface of the ocean. Above the surface of the Earth, it gets a little harder to work with satellite winds. Although, if you've got little clouds, you can track individual cloud elements, and then, working on the assumption that the clouds are, being pushed by the wind, then you can figure out the winds. The satellites in geostationary orbit take satellite pictures of the clouds maybe every 5 minutes on average. It might be 2.5 minutes nowadays. And, okay, if an algorithm can go through and identify a single cloud element, here is a single tiny cloud, and then, 2.5 minutes later or 5 minutes later, it can see it move to this location. There are ways to determine the height of the cloud, and then change the position of the cloud, and we can figure out then the winds. That's called a cloud-tracked wind. And so that can be a very powerful tool, especially over the oceans, for augmenting what we know about the winds. And these all can be part of the databases that you would be working with. Remote sensing is totally cool stuff. And like I said, there's, I think, 2 or 3 whole courses on the books at Creighton about remote sensing. Plenty of people get their master's or PhD in remote sensing. It's a big deal. And so in like 20 minutes, there's only so much I can tell you about it. We are finally done with this huge lecture. I apologize that it took 180 some slides to get through all of this stuff, but as you saw, it was like a 20-page section of your book. Let's do a couple quick questions about what you saw, just to kind of hit on a few key points. Question 13, which of the following is an example of passive remote sensing? Lidar, satellite pictures, Doppler weather radar, or salameters? Which of those is passive remote sensing? Make a choice from those 4 options and get a little feedback before we move on to question 14.